Today, we are going to focus on the next application of derivatives, and that focus is going to be on particle motion. And specifically, we are going to look at particle motion problems that deal with particles that are moving along the x or the y axis. So more of a horizontal or vertical movement. Now, what's important to remember is when you're given the graph of particle movement, that graph does not represent the motion of the particle. The particle will always be moving along the axis. And most of the time, we're going to speak about movement along the x-axis or the horizontal motion of particles. Okay, and that's important because we're just looking at a straight movement. In this lesson, we are going to make sure that we develop the ideas of velocity and acceleration in terms of position. And we are going to look at two different types of velocities and acceleration. So the first thing we're going to look at is velocity, all right? And what's important is regardless of what type of velocity you have, all right, velocity is the rate of change of position. So that brings up a very, very important word here, rate of change. We've spoken about rate of change multiple times, all right? And we know from Algebra 1 that rate of change represents slope. So how does that relate to what we are talking about in calculus? Well, it's all based off of the two different types of velocities. So if you're ever asked to find the average velocity of a particle, and it's within the interval a to b, okay, you should automatically be thinking AROC, the average rate of change, which we know we find by finding the slope of the particle from A to B in regards to position, all right, where P of t is the position. Now, if they're asking for the instantaneous velocity, and remember, that is at some point. So here we have IROC. Well, this is the first derivative of the position at that c value. Okay, so let's look at an example of this. A particle's motion is given by the function P of t is equal to e to the t sine t, where P of t is measured in centimeters and t is measured in seconds. Answer the following questions. What is the average velocity on the interval from 1 to 3? Indicate appropriate units of measure. Okay, so if we're being asked to find the average velocity, we're looking at AROC, and it's on the interval from 1 to 3. So it's going to be P of 1 minus P of 3 all over 1 minus 3. So P of 1 minus P of 3, we're going to have to use our calculator here and get negative 0.47 divided by negative 2. So our average rate of change is 0.274 centimeters per second. Okay. Now, let's look at how that differs with instantaneous velocity. Instantaneous velocity means we need to find the first derivative, okay, and plug in the c value of 1.5. So go ahead and find the first derivative of this function. if you did this correctly, you would have recognized that you have to use the product rule in order to find the first derivative. So the first derivative would be e of t times 1 sine t plus e of t cosine of t. Okay, so that's our first derivative. And now to find the instantaneous velocity, we're going to plug in 1.5 for t into our first derivative equation. And we would get 4.787 centimeters per second. So once again, if you're asked to find the average velocity, you're doing AROC. If you're asked to find the instantaneous velocity, you're doing the first derivative. And this is always with respect to position. So, before we proceed, a connection needs to be made. When given the function f of x, how do we find the slope of the secant line? Okay, in terms of position of a particle, what does the slope of the secant line correspond to? What does the slope of the instantaneous velocity correspond to? All right. Well, hopefully we remember that the slope of the secant is equal to the average rate of change because it's across an interval between 2 points. All right. So that would be the position of A minus the position of B all over A minus B. So the slope of the secant represents the average velocity, whereas the slope of the tangent, which we have said on multiple occasions is equal to IROC, or the average rate of change, which is the first derivative, that is equal to the instantaneous velocity. So now that we've recognized that the instantaneous velocity is the first derivative of position, we need to talk about acceleration. All right, and there too is two types of accelerations. Now, what's important is that acceleration is the rate of change of velocity. All right, it's the rate of change of velocity. So the average acceleration, which right away you should say, okay, well, we're talking about AROC here, is equal to V of A minus V of B all over A minus B. All right, where V of T is equal to the first derivative of position. All right, and the instantaneous acceleration, which is IROC, and it occurs at a specific time of c, that's equal to the first derivative of velocity at c, or the second derivative of position at c. Okay? So if we go back to our problem that a particle's position is given by the function p of t is equal to e raised to the t power sine t, where p of t is measured in centimeters and t is measured in seconds, we need to answer the following questions. So the first question is, what is the average acceleration on the interval from t equals 1 to t equals 3? And the second question is the instantaneous acceleration. All right, so I'm going to have you guys do that now. But remember, when we're finding its acceleration, its rate of change with respect to the velocity. So remember, we found the velocity equation as v of t is equal to e to the t sine t plus e to the t cosine t. So go ahead and find the average acceleration and the instantaneous acceleration. So now that we've identified the relationships between acceleration, velocity, and position, let's summarize what we know. So we know that the original function always corresponds with position. The first derivative of position corresponds with velocity. And the second derivative of the position function corresponds with acceleration. Now, very, very important, all right, remember that this is all instantaneous velocity and instantaneous acceleration. So, let's talk about what we know. If the velocity is 0 or undefined, which means that the first derivative equals 0 or undefined, well, we need to go back to what we know. If the first derivative is equal to 0, we know that that has a relative max or min for the original function, which means what with regards to position? That means that this has a potential turnaround point. If the velocity, which is the first derivative, is greater than 0, we know our position is increasing. And what that means is it's moving further and further away from the starting point. If it's less than 0, then that means our position is decreasing, which means we are closer to our starting point. If it changes from positive to negative, it means we are changing from increasing to decreasing. And if it changes from negative to positive, it means we are changing from decreasing to increasing. Everything that we've talked about with the first derivative test applies to position and velocity. It also applies to the relationship between acceleration and velocity. So if acceleration, which is the second derivative, is equal to 0 or is undefined, that means that this is where a potential change in velocity has occurred. Boy, sorry guys. All right. If our acceleration is greater than 0, that means our velocity is increasing. If our acceleration is less than 0, that means our velocity is decreasing. And if it changes from positive to negative, it is changing from increasing to decreasing. So let's look at this relationship on a graph. The graph below represents the position of a particle which is moving along the x-axis, at which point is the velocity equal to 0. Now remember, velocity represents the first derivative. So when is the first derivative equal to 0? Well, we know that that would result in a horizontal tangent. So there would be 2 points at which the velocity is 0. The first point, so the velocity of t equals 0 at points B and D, because S of t has a relative max or min there. Okay? Let's look at the second question. At which points does the acceleration equal 0? Now in this case, we're saying our second derivative equals 0, which means if we remember, those are points of inflection where our graph changes concavity. So where does our graph change concavity? Well, clearly the only point there is where it changes concavity is at point C, because S of t has a point of inflection. Okay? So, on what intervals is the particle's velocity positive? All right, so they're asking when is the first derivative of this function when is the first derivative of this function greater than 0? Well, that means that the original function must be increasing. So, the velocity is going to be greater than 0 on which intervals? Well, it's going to be from 0 to b and from d to positive infinity, because our original function is increasing. And remember, we start at 0 and not negative infinity, because the smallest time is going to be 0. All right, now what I'd like you to do is answer the next 3 questions of this, the next 2 questions, 3 questions on this graph. When is the particle's velocity negative? When is the particle's acceleration positive? When is the particle's acceleration negative? So now that we've been able to make connections between the first and second derivative tests with particle motion, we want to talk about the 5 commandments of particle motion. So these are commandments that you will always want to remember, always. So the first commandment, and this is in reference to particles moving along the x-axis. So the first is if your velocity is positive, the particle is moving right. Which means the opposite is true as well. If the velocity is less than 0, we know the particle is moving right. Is moving left. All right, now, if velocity and acceleration have the same sign at time t, the speed of the particle is increasing. If the velocity and acceleration have opposite signs at x equals t, the speed of the particle is decreasing. Okay? Now, finally, if the velocity is equal to 0, but the acceleration is not equal to 0, the particle is momentarily stopped and is changing directions. These 5 commandments of particle motion are something you're going to be using often when solving these types of problems. So let's look at an example together. Suppose the velocity of a particle is given by the function v of t is equal to t plus 2 times t plus 4 squared, where t is measured in minutes and v of t is measured in inches per minute. Answer questions below. So the first thing they want you to answer is, what is the velocity at 3? So this is an easy problem where all you have to do is plug in 3 for t. So we get 5 times 7 squared, and that would be 245 inches per minute. Now it's your turn to find v prime 3. V prime 3. So go ahead and find the first derivative and plug in 3. So hopefully you found v prime 3 to be 119 inches per minute squared. So when it's asking about the speed of the particle, okay, we need to determine whether it's increasing or decreasing. Well, the velocity is positive, the acceleration is positive, they both have the same sign, which therefore means the speed is increasing because v prime 3 is greater than 0 and v of 3 is greater than 0. And remember, v prime 3 is equal to the acceleration. Okay? So now you can answer the next question. On what interval is the particle moving to the left? On what interval is the particle moving to the right? Once you are done with these questions, you are free to go work on your homework worksheet. Have a great weekend, everybody.